Hello friends, let us study the orthogonal property of Bessel function. So the statement of the orthogonal property of Bessel function is if we have alpha and beta as the two distinct roots of Jn of x, then integration from 0 to 1 x into Jn of alpha x into Jn of beta x with respect to x will give 0 if alpha not equal to beta, and it is half of jn dash of alpha whole square if alpha is equal to beta. Now let us see the proof of this. Now we'll consider the Bessel equation x square u double dash plus x into u dash plus alpha square x square minus n square into u equal to 0. The solution of this equation is u equal to Jn of alpha x, and the other equation written in terms of v is that x square v double dash plus x into v dash plus beta square x square minus n square into v equal to 0. The solution of this equation will be v equal to Jn of beta x. Now let us multiply this equation 1 by v by x and equation 2 by u by x and subtract. Now multiplying by v by x for the first equation gives x into v u double dash, 1x cancels, here x cancels again, we have v into u dash, splitting this alpha square x square u multiplied by v by x means we get alpha square x u into v, and last term minus n square u multiplied by v by x, it is minus n square u v by x. Second equation now will multiply by u by x, 1x cancels, we have x u v double dash here. Second term x v dash multiplied by u by x, x cancels, we are remained with u into v dash. Then again we'll split this beta square x square v multiplied by u by x, we get beta square u v x, and last term minus n square v into u by x, we get minus n square u v by x. RHS terms are zeros. Now let us subtract these two equations. You can see last terms are same, they get cancelled with different signs here. Now the remaining terms, let us write them. In this first terms, x is common. If you take it outside, we have v u double dash minus u v double dash. Second terms, we have v u dash minus u v dash here. In these terms, if you take uvx common, we have alpha square minus beta square. RHS is 0. Now these two terms together can be written as derivative of x into vu dash minus u v dash. If you differentiate this term vu dash minus u v dash multiplied by x, then we will be getting these two terms. Then here the term is taken on the RHS, we'll write it as beta square minus alpha square into uvx. Now let us integrate this equation with respect to x between 0 to 1. Now integration and differentiation cancels. We are remained with the function x into vu dash minus uv dash. In the limits of integration are from 0 to 1. RHS beta square minus alpha square is constant. Integration from 0 to 1 of uvx. If we put the upper limit 1 here, 1 into this bracket term, we are remained with v u dash minus u v dash. If we put 0, we get a 0 here. So we have v u dash minus u v dash because they are functions of x again. So we'll write they at x equal to 1 here. Then RHS is kept as it is. Now we know that u means jn of alpha x. If we differentiate, then u dash is alpha into jn dash of alpha x. V is jn of beta x. If we differentiate this, v dash is beta into jn dash of beta x. Now let us substitute these in this equation 3. We have v u dash. So v means it is jn of beta x. U dash means it is derivative of u. that is derivative of jn of alpha x, jn dash of alpha x into the derivative of alpha x, we have alpha, already it is written. Now here minus, it is u into v dash at x equal to 1. Again RHS term, beta square minus alpha square, integration from 0 to 1, x into u v we have. So jn of alpha x into jn of beta x integrated with respect to x. Now from the Bessel orthogonal property of Bessel equation, Bessel function, we need this integration term. So let us take it on the LHS. Integration from 0 to 1, x into jn of alpha x into jn of beta x dx. It is equal to, taking this beta square minus alpha square on the other side, we have 1 upon beta square minus alpha square multiplied by this whole bracket term at x equal to 1 is there. So if we put x equal to 1 here, we have alpha jn of beta into jn dash of alpha minus beta jn of alpha into jn dash of beta after putting x equal to 1. Now let us call it as equation 4. Now we'll take two cases. Suppose beta not equal to alpha and suppose beta equal to alpha. The first case, if we consider beta not equal to alpha, then here, since alpha and beta are the roots, we know that jn of alpha is 0 and jn of beta is 0. If we put those, the numerator term becomes 0 and the denominator is not 0 because beta is not equal to alpha. Hence, the RHS of equation 4 reduces to 0 whenever beta is not equal to alpha. Now consider the second case for beta equal to alpha. Now, if we take beta equal to alpha in this equation 4, already we have seen that numerator is 0 for the whole term here. Jn of beta and jn of alpha are 0, so whole term becomes 0. If alpha is equal to beta, denominator also becomes 0. Hence, equation 4 takes 0 by 0 form. That is, it takes indeterminate form. Hence, we evaluate this equation 4 for beta equal to alpha by taking the limit as beta tends to alpha on both sides. Now just limit as beta tends to alpha of LHS, again limit as beta tends to alpha of the RHS term. Now considering alpha as a root, as a constant one, we have gn of alpha is equal to 0 and beta is considered as a variable which approaches alpha because we are taking limit as beta tends to alpha. Since alpha is a root, we have jn of alpha is 0 and we take beta tends to alpha here. So beta is a variable which is approaching alpha. Now if we take that here, then instead of beta, we'll substitute alpha, so it becomes jn of alpha x into jn of alpha x, that is jn of alpha x whole square multiplied by x. RHS term, now we have here jn of alpha which is 0, so second term reduces to 0. The first term we are remained with alpha jn of beta into jn dash of alpha divided by beta square minus alpha square. Now this again terms 0 by 0 if we put beta as alpha. Beta tends to alpha is there. If we put beta as alpha, again we get jn of alpha which becomes 0 and denominator if we put beta as alpha, alpha square minus alpha square means it becomes 0. So again it takes 0 by 0 form. Now to evaluate this, let us apply L'Hospital's rule and differentiate with respect to beta. Now LHS is kept as it is. In the RHS, it is differentiated with respect to beta. Alpha constant, jn dash of alpha is constant. Derivative of jn of beta, it is jn dash of beta. Denominator is beta square minus alpha square. Derivative of beta square is 2 beta. Alpha is constant, so derivative becomes 0. Now, if we put beta as alpha here, we get alpha jn dash of beta into jn dash of alpha into jn dash of alpha, which is jn dash of alpha whole square, and denominator again we are putting beta as alpha, so it becomes 2 times alpha. Alpha cancels, we are remained with jn dash of alpha whole square divided by 2. Hence, integration from 0 to 1 x into jn of alpha x into jn of beta x dx will become integration from 0 to 1 x into jn of alpha x whole square dx, which is equal to jn dash of alpha whole square divided by 2 for alpha is equal to beta. Thus, we get this orthogonal property of the Bessel function, which is 0 for alpha not equal to beta, and which is half of jn dash of alpha whole square for alpha is equal to beta.